Okay. Attention everyone. So Structural Lake, her and I have an agreement. She's trying to finish her PhD, so I picked a few recitations out of the year, the semester that I'll take to allow her to write her thesis and stuff. So you're stuck with me today then. So we're going to go through two different problems, just practice problems, the ones that I just handed out. Anyone come in late and not get one? All right. So practice problem is fairly well related to work that we just talked about. And so the first problem, and we'll try and make this as interactive as possible. The first problem we have, what we've been discussing all along, we've been calling something that's a physical system. We're trying to control the plant, right? And so it's stating that you have some sort of physical system. This is just a simple motor. And we're trying to get into ideas of how do you write feedback control systems for plants. And this is saying this is just a simple motor. And it has this transfer function. And that's really not very clear, is it? Can you read that in the back? Yeah. Any advice on how to do that? Classroom controls. Display. I don't know if my controls here are going to help anything. Let's see. Brightness is all the way up.
There's switches on the wall.
Yeah, these are for the lights, which I think is only going to make, I turn this on even worse, right? So, is that better? Yeah. Okay. A little bit better. Still not great, right? Now it's turning on. Okay. So I hope that's reasonably legible. So maybe I'll just blow it up in size to compensate for that. Okay, so this idea that we have a plant, much like what we've been working with before, we had an example in lecture. We had a mass spring damper, right? A really simple model of a motor. We looked at proportional control, and we looked at kind of the forward direction of understanding if we have certain plant parameters, how that's going to affect the response. Now we're going to go in the reverse. We're going to say, all right, we have some sort of response. How do we then back out maybe what a parameter of our plant is? And then the other difference between this system and the system we talked about in class, that system had a spring, always dragging the system back to some neutral position. And this system does not. Okay, so it's a little bit different, but it's fairly similar to what we've been talking about thus far in class. And so then the question is, if we have some sort of unknown parameter k tau, and we put this system in some sort of feedback loop with a very simple controller, so we say a proportional controller with a gain of 1, and then we do some sort of experiment, can we back out this unknown parameter, right? That's what we're trying to look at here. And so this experiment is we're putting in a step in reference. Okay, so what we're saying is, motor system at time of 0, go from a position of 0 to a position of 1 in 1 radians. Right? So instructing a motor to go to a certain position is what we're trying to do here. And then we want to say, all right, with this experiment, then try and back out these parameters. So this experiment is shown here. So zooming in. At a time of 0 seconds, we turn the system on. It has some sort of response to it. And this is what it looks like. And so now we want to say, all right, we knew a few things. We knew some of the parameters of the system. We knew what the feedback control gain was. We knew what the input was. The input was a step function. So it means that the input to the system looks like this. And for time less than 0, it was 0. All right, now what is k tau? All right, we're going to try and figure out and back out what this is from this experiment. Okay. Any questions on my kind of the problem setup? Okay. All right, so we're going to work on this and we're trying to figure out how to solve this. So what do you suggest we do, in terms of what pieces of information do we have, what pieces of information do we need to try and solve this problem. What do we have? Yes? Yes, we would be, yeah. Okay, so we could figure out, so we have this experiment, right? We have a few things that we've learned so far in class, right? We learned about the settling time in terms of a metric of a time domain response. We talked about rise time, we talked about overshoot. We talked about the C final value. The system does have a spring. It's not going to be too helpful to find us the C final value as it equals 1. But yeah, so we have some of this information available to us from the experiment. Right? So we can go the settling time route. The difficulty with the settling time route is it's a little bit difficult to assess at what time this is completely settled. So we may want to think about other metrics that may be a little bit easier to pick off the plot. But I agree that we should be looking at the plot, right? And we can look at some of these values and try to understand those relationships. So settling time, I'm telling you, is going to be a little difficult. Other suggestions maybe of things we could look at? Yeah, so here it only goes in the positive direction. So yeah, so we're good there. So we heard overshoot here, right, in the front. So we can look at the percent overshoot. And this is all going to be estimates. All right, so this would be the very peak of this response. And so this is around 1.35, right? If you remember the equation for overshoot, this equals C max minus C final over C final. Right, so in this case, we have C max is 1.35 minus 1 over 1. This is approximately a 35% overshoot. For this, what other metrics could we pick off of this? Rise time, right? Would be another one that would work, right? So the rise time, what's the definition of rise time? Yes. Louder so the whole class can hear. Yeah, exactly. So, yes, the time it takes for the response to get within 90% of the new steady state value. So here's the old steady state value, here's the new steady state value. And so then the rise time would be approximately in here. This would be our rise time for the response. So what is that about? I heard something about 0.6? Yeah. So somewhere around 0.6. So these are all estimates off a plot, but we could say the rise time is approximately equal to 0.6. Okay. So we have some things to work with. Really we have, between the overshoot and the rise time, we have multiple ways to actually get at what this unknown parameter may be. Okay. All right. So once we have that, what else should we do? We're to try and understand what k tau is. Yes. Exactly. Yeah. All right. So we can relate this. Okay, we said that this response looks a lot like a second order underdamped response. It is exactly a second order underdamped response. And so given these relationships that we know, second order underdamped system is going to have a rise time that's approximately equal to 1.8 over the natural frequency from some of the rules of thumb that we've established. So if we have that, we could say that rise time approximately equal to 1.8 over the natural frequency, or natural frequency is approximately equal to 1.8 over the rise time. Right. And so we said that the rise time measured from this plot was approximately 1.6, so we'd say then the natural frequency is approximately 3 radians per second. Any questions about that idea in terms of how, if we see a responsive system, we can start to understand some of these metrics in terms of either damping or natural frequency, etc. Okay, so we know what the natural frequency is, right, of a system. So what do we do now? How can we potentially tie that to, we have a plant, which is not a second order underdamped system, right? There is no s to the 0 term in this. But this is not what we're showing in this response. This was not looking at the step response of the plant. This is looking at the step response of the feedback loop. So how could we try and understand what the natural frequency of the combined integrated system looks like? Yeah, exactly. So this transfer function here is just the plant. This is just what we typically call in this class G2 of S, or the plant. Right? This is the system we're trying to control. And this is just one element of the entire feedback loop, right? So just like Instructor Lake brought all this equipment in last week, and she also had some examples of other hardware, right? This is explaining an experiment where you have all this hardware assembled, sensors, actuators, plants, data acquisition systems, all those things are all put together and you run this experiment. So the plant is just one element of that, right? It's not the entire system. So we want to come up with, as Justin recommended, the transfer function for the entire integrated system, right? So Justin, what is that transfer function? Yeah, so what's the block diagram reduction? So we say, yeah, so if we have our output in this case is the position of the motor, the input is the reference, so you're saying it's K of S yeah, so we could, but we actually know the form of this, right? Okay. So we can now, we also know K of S, that's given in the first part of this, parts, what we call A. So we know this is a pretty simple one. This is proportional control with a gain of 1. This is pretty simple. So if we were to now insert the values that we know, all right, now what do you recommend we, Justin, following up on that thought, what would you recommend multiplying top and bottom by? Yeah, exactly. So we multiply top and bottom. So now this looks like it's in our standard form for a second order underdamped response system. So just to note, our plant itself is not second order underdamped, right? It's actually a system with a pure integrator and a real pole in it. So when we put it in a feedback loop, it becomes something completely different. Okay. So just because you start with a plant that's of certain characteristic, doesn't mean when you put in the feedback loop it's going to have the same characteristics as being second order underdamped. It actually can change completely. Okay. So then matching this up, so we say that, sorry, I'm spanning 2 pages here. I don't know if that's going to be confusing or not, but our prototypical second order underdamped system has this form. Okay. So what is then K tau? Heard it up front. Someone said 9. Right, so it's 9, right? So we said that the natural frequency, as observed from the experiment performed, was 3. Right, so that means that at K tau, yes?
So does that mean the natural frequency of our plant is also the natural frequency of like our overall feedback loop?
Our plant doesn't have a natural frequency associated. So it's natural frequency is really only defined for a second order underdamped system. So this is of a completely different form.
So was the plot for the closed, was the plot for the feedback control system?
The plot was for the feedback control system. Okay, so by doing these relationships, comparing these two, we would say that K tau, everything here is an estimate, right? We say that K tau would be estimated to be 9 in this example. Other things that we can look at here. So we know what the natural frequency is, and we know what the s to the 1 term is. So we can estimate what zeta is for this plot as well and make sure it matches, that everything agrees with what we expect it to be, right? So we have matching s to the 1 term. We have that 3/2 equals 2 zeta omega n. All right, so omega n is equal to 3. So that means this 3 and this 3 cancels. That means that zeta is approximately equal to 1/4. Okay, so there's this long expression for the relationship between overshoot and zeta. You can use that if you want, but it's probably easier just to use this map. And so if we said that we had a zeta of 1/4, right, this would be right around here, right? This would be 0.3, this would be 1/4. Hold up, that's really large. Okay, so our estimates may be a little off. All right. We would, how's this so off? Did I do my math correctly here? That looks right. Okay. I mean, the estimate is worse than I thought it would be, but we would be at somewhere in the order of 40 to 45% in terms of overshoot, and we were at 35. So we're a little off, but in terms of our estimates, our natural frequency may be not quite 3, something close to it, but it's somewhere in the shooting distance, we'd say, right? In terms of matching these up. Okay. Any questions about part A of that one? Okay. All right. To note, I guess really quick, there's no spring in the system, and so that results actually in the steady state value reaching its intended target. We'll talk a lot about that on Friday. Yeah, Friday. For those of you who are not already south of Ohio on spring break, we'll talk about the reason why that is. Second part of this problem is asking, okay, so now, and this is, I don't want to spend too much time on this because this is pretty well related to other problems that we looked at thus far in class. But basically, this is getting towards the idea of design. It's probably, we can't get to design yet because we don't have the right background knowledge just yet, but it says, okay, we want to now create a system that instead of having this behavior has a slightly better behavior. We want that the rise time to be 0.6 seconds, which it already is, but that the overshoot to go down. We want the overshoot to go down to 15%. So the question is, in this complex plane, where should we, if we have the ability via feedback control to move around the poles, where should we move them to? Okay, so we already said that 0.6 for rise time corresponds to a natural frequency of 3, right? So that we've already established, so we can start to window out the complex plane and say this is going to be our barrier, natural frequency of 3. And then we also want to establish that we want to have a overshoot less than 15%. So looking at this map, 15% overshoot going over corresponds to a zeta of around 0.5, right, for kind of a rough approximation. And so this is directly from MATLAB, where they'll often plot level sets of zeta on a map for you if you use the grid function for pole zero maps. So that would be this region. And so then we would say that we want to put our poles somewhere in this region to satisfy those design requirements. So we'll talk about maps that look a lot like this kind of fan pattern often in this class. We're usually trying to push the poles to the left and also closer to the real axis. And we'll talk a little bit about how it's almost impossible to actually move the poles all the way to the real axis. You're trying to kind of squeeze it into a certain range of the complex plane.
That's to reduce the oscillation.
Exactly. Yeah. So it's in general, especially talking about thermal systems, mechanical systems, oscillations in your system are usually a bad thing. That's why things rattle, right? Yeah. And have wear. Okay, any questions on that problem before we move to a different one? Okay. So the next problem is getting to these ideas of basically the relationships between second order underdamped systems and when we start to add poles and zeros to the system. So what this problem is asking, it says, here are all these pole zero maps as potential options, and then it's giving you a set of step responses and trying to understand, all right, which step response matches the set of pole zero maps. So this is on midterm 1, we have in the review packet, there was a problem quite like this, but that was only with basically, I think 2 poles at max. And so this is taking a step further. Now we're talking about how additional poles and zeros affect the system. What does these additional poles and zeros have in terms of influence on the response? And so we have a few cases that look familiar and a few that are new information as of Monday and this morning. So this would be example of two complex conjugate poles, and this would be example of having two real poles. And then we have a few different variants of these responses here. So the step responses are on the back side of that sheet. And here are the different step responses. Okay? So we're trying to match between the two. Okay. And so given what we learned this morning and given what we learned on Monday, I guess we're looking for some thoughts on how we're going to go about solving this problem. What do you think, Sierra?
So based on what we learned this morning, the only one that has a 0 in the right half plane would be the fifth one, which is E, that would go negative first, so it should match with D.
Exactly. Yeah. So what we learned this morning, if a system has, well, I guess we'll say if a system has a 0 in the right half plane, it may go in the negative direction first. Not always, it depends on the location of that 0, but if you see a response going in the negative direction first, it must have a 0 in the right half plane, right? So if we look at D, in terms of saying something that is unique amongst all of these responses here, we know that this must correspond to a 0 in the right half plane, and there's only one of those here. All right, so we would say that 5 is equal to D. Right? So that checks one off. What else do we see here? Justin.
So for like C and F, they're both like kind of second order underdamped, and for 1 and 2 on the poles, those are like for 2, it shows that the like 2 lower poles are kind of canceled out, and that the like higher ones would have a larger omega n. So would you be able to say that Q corresponds to C?
Okay. So you're comparing C and F in 1 and 2. Is that what you're saying? Just so. Okay. All right. So Justin is identifying that we have two plots here that look like they're second order underdamped responses, right? And so one, you're saying, has a higher frequency than the other one, right? So you have, in terms of the period of oscillation here, this is a smaller period of oscillation than F, and so therefore a higher frequency, right? That's the comparison you're making. Okay, and then he's comparing which one? You're comparing 1 and 2 then? Yeah. Okay, so you have a case of comparison of 1 and 2. So you have two poles here at negative 0.5 plus or minus, it's about 1. And you have the same situation here, but you have pole 0 cancellations, right? Okay, so pole 0 cancellation, as we learned this morning, that cancels the influence of that pole at that location. So you're saying that 2 behaves more like a system with lower damping ratio, damping constant, and higher natural frequency. That's the claim? Okay, I agree with that. We'll talk about this one in a second, but you're right to say that this one's going to have the highest natural frequency or also highest damped natural frequency, depending on how you want to look at it. Right? So, is there any questions about the idea about how we're comparing the case where this one has, in the upper left, 2 complex conjugate poles. 2 has a case where you have a total of 4 complex conjugate poles, but 2 of them are canceled by zeros. So it acts like a system with just 2 complex conjugate poles, but these are farther up and down the imaginary axis. Okay. So I agree that 2 is equal to C. I am on board with that one. Okay, so then my only question is, what about the comparison between 1 and 6? maybe you want to pull up your notes from this morning, but what does a 0 in the left half plane do to a second order underdamped system, especially if it's close to the head of the center part? Yes?
It increases the overshoot, so I think 6 would correspond to that.
So if you have a 0 in the left half plane, it increases the overshoot. And so we have, even though this one is not as obvious as a second order underdamped response, it still has basically a rise and an overshoot associated with it, right? And then we have, as a comparison, one with a larger overshoot. Right? So comparing the two, given the fact that the pole locations are exactly the same locations, we would say that 1 corresponds to E, and then 6 corresponds to F. Any questions about that?
Does the presence of the 0 in the left half plane change the natural frequency of the system?
So we wouldn't say, natural frequency is only defined for second order underdamped systems. So we're saying that the response is going to be approximately like a second order underdamped system, but it's not actually a second order underdamped system. It's modified from that. So we could say it changes the effective natural frequency of the system.
So like we're still modeling it as a second order underdamped system?
We're saying it behaves approximately the same. The overshoot here, if you look at F, the overshoot has increased dramatically in comparison. So before the overshoot was pretty minimal, maybe we're at somewhere around 25%, and now we're all the way up to 75% by adding this 0 here. So it has some other features that are different. So we get kind of an overshoot that we would not expect from the pole locations we have because of 0 isn't there. Okay. All right. And we saved the easiest two for last. So what's the difference between these two then?
This formula faster less time.
Yeah, exactly. Yeah. So because both of these are going to act like first order systems, we'd actually refer to this as being a time constant. Usually we talk about first order systems in terms of time constants. Right? Yeah. So we have two comparison cases. Both have real poles in exactly the same location, but this one, number 4, is being canceled, right? So in terms of effective response, this behaves like a pole farther to the left. This one, the pole closest to the origin is what dominates, right? So whatever's closest to the origin is going to have the largest effect. So this is going to act like more like a single slow pole. This is going to act like a single fast pole in terms of responses. So if we look at these two cases, we have one that responds quickly, or actually a fast pole, and one that responds and takes a little bit longer time. So the fast one is going to be equal to A, and then the slow one is going to be equal to B. Any questions about those ideas in terms of how additional poles and zeros interact with the system? Okay, quiz time.